In this module, we will consider forces in uniform and non-uniform circular motion. When an object moves along a curved path through space, any acceleration that is perpendicular to the path can be thought of as a centripetal acceleration. This acceleration, like any acceleration, must be caused by a net force in the direction of the centripetal acceleration. This force is called the centripetal force. Because of the form of Newton's laws, clearly more than one force can combine to yield the centripetal force, because any acceleration can be due to a net force. Also, we must keep in mind that only the part of a force that is parallel to the centripetal acceleration can contribute to the centripetal force. Let's consider the simplest example of this. Assume we have a flat, frictionless table on which a mass sits and can move around, and we constrain the mass to move by placing a string along it fixed at some point, and we give the mass a speed, and this will cause the object to undergo uniform circular motion with the centripetal acceleration given by the usual formula that it's equal to the speed squared divided by the radius, in this case, the length of the string, L. Now, the centripetal force that causes this acceleration will be caused by tension in the string. And we can easily use Newton's laws of motion to tell us that the force, the net force caused by tension in the string, is mass times acceleration. And we know that the acceleration is v squared over L. And so this tells us what the tension in the string is. Now, let's assume that the mass on the end of the string of length L is swinging freely in a circle in a vertical plane. Because of gravity, the speed of the object will no longer be constant. So we no longer have uniform circular motion, but we have still circular motion, but where the velocity depends on the angle theta measured from the vertical direction. The centripetal acceleration will be given by the same formula, but now the speed will depend on the angle theta. Also, the centripetal force that causes this acceleration will be caused now both by the tension in the string and by the force of gravity. Let's consider a free body diagram for the mass on the end of the string. We see the velocity here. We're drawing this just to give us indication of the direction, but there will be a tension acting along the radial direction, and there will be the force of gravity acting down. And we know that we want to decompose the forces acting on the mass into those which are parallel and perpendicular to the direction of the centripetal acceleration. So we will choose our I hat, j hat vectors in the following way. And notice that we have them given as functions of theta, because depending on the angle of the mass in its circular motion, these directions will point in different directions. J will always be in the radial direction and I perpendicular to that. Now, the centripetal acceleration can be written with the usual formula, but the velocity, or rather the speed, will be a function of theta, and the direction will also be a function of theta. The tension will be minus the magnitude of the tension in the j hat direction, but these again, the actual direction and the magnitude will depend on theta. And we can always decompose the force of gravity. While the force of gravity is constant, regardless of the angle theta, the components of it will actually be functions of theta. So we write it as if it were a function of theta. But if we were to calculate the magnitude of the force, it would be a constant. Now, we can write out the equations for Newton's second law for the directions parallel to the centripetal acceleration. And that tells us that mass times the centripetal acceleration is going to be equal to the tension minus mg cosine theta in the j hat direction. And if we plug in values for the magnitudes of these and drop the j hat of theta, we see that the centripetal acceleration times mass with a minus sign is equal to minus the tension minus mg cosine theta. And we can now solve for the tension as a function of theta, and we get the mass times the quantity. Well, we have the centripetal acceleration minus the gravitational acceleration times cosine theta. Let's consider this in some examples. What happens if we consider the mass to be at the very top of the circle where theta is equal to 0? Cosine of 0 is 1, and we see that at the top that the tension is equal to m times v squared over L minus g. Now, if the object is moving fast enough, so v is large, then v squared over L will be larger than g, and we will have a positive tension, and the object will move in circular motion. But notice that if the speed becomes small enough, there is a point at which v squared over L will become equal to the gravitational acceleration, and the tension goes to 0. Now, this is still a situation where we can have circular motion. The mass will continue through this angle and continue moving around in a circle, but the tension will just happen to go to 0 at the top of the circle. But what happens if the object is going even more slowly at the top, so that v squared over L is less than g? This would suggest that there is a negative tension, but we know that there can't be a negative tension in a string. String only supports a positive tension where you're pulling along the length. You can't push with a string. So what does this actually mean? Well, what we have to have is if the tension is 0, then for Newton's laws of motion to apply, then the centripetal acceleration, v squared over L, must actually be larger than we think it is. What this means is that the radius of curvature, which the object is actually following in this case, is not the length of the string, but something smaller, so that the acceleration is larger, and in fact, v squared over this radius will be equal to g, so that the tension can be 0. Now, if we happen to be halfway down the circle at 90 degrees, then gravity doesn't contribute at all to the tension. It's all due to v squared over L. Finally, when the mass is at the bottom of the circular path, the tension is going to be given by the sum of v squared over L and g, and it doesn't matter how fast the object is moving, it's always going to have a positive tension.